Hello everyone, in the last video we talked about derivatives and integrals, and in today's video we're going to talk about differential equations. We are going to see the definition of differential equations, different types of differential equations, how to tell them apart, and of course some examples. So let's get into it. Let's see some examples of commonly found differential equations in physics. The first here I'm sure many of you are familiar with. It describes a body attached to a spring and spring force. The second here is also a very common differential equation. It describes waves, like this electromagnetic wave here on the left. And of course, Schrödinger's equation, which many of you might be familiar with. Okay, so what is actually a differential equation? Well, it is an equation that relates one or more unknown functions and their derivatives. So let's say that I have a function f of x and its derivatives, the first derivative, the second derivative, and so on. And of course, you can also use this symbolism here. So the first, the second derivative, and so on. And I want to relate this function to these derivatives. So an example of a differential equation could be f of x plus the first derivative of f plus 5 equals 0. Or for example, it could be f of x minus x times the first derivative plus x squared equals 0. Or a third example, I could have a more complicated equation that could say, for example, the first derivative plus f plus the sine of x plus x to the third power equals 7, for example. These are all random examples of differential equations. So now let's see some of the main differences between algebraic and differential equations. Algebraic equations are some equations that you are already familiar with, for example, polynomial equations or other algebraic equations that you have already seen. So the main difference is, of course, that algebraic equations do not contain derivatives, whereas differential equations do contain derivatives of an unknown function. Now, the other difference is that the solution to algebraic equations are numbers. For example, a singular number or a set of numbers. But the solutions to differential equations are functions. Okay, so let's see an example of this. I have an algebraic and a differential equation here. And let's say I go to solve this one, which I will do by factoring. And I know that the solution is a number. But if I go to solve this equation here, essentially what I'm trying to find is a function which is equal to its derivative. So the solution to this equation naturally will be a function, because what I'm looking for is a function, whereas in algebraic equations what I'm looking for is a number or a set of numbers. Okay, so let's see how many different types of differential equations there are and how do we classify them. We classify them based on order, type, linearity, and homogeneity. So let's see what these terms are. Okay, so let's see how we classify differential equations based on order. What is the order of a differential equation? It is the highest order of derivative of the unknown function that appears in the differential equation. So if I have an equation that only contains first-order derivatives, it is a first-order differential equation. If it also contains second-order derivatives, it is a second-order differential equation. If it also contains third-order derivatives, it is a third-order differential equation, and so on. The general form for a first-order differential equation is this one on the left, and here on the right we have the general form for a second-order differential equation. Now here we have y being the unknown function, p, q, and r that you see here are functions of x. So some examples of this. For example, a first-order differential equation could be the first derivative of the unknown function times x, y, and y is the unknown function, equals x squared plus 5. And an example of a second-order differential equation could be this one, where I have the second derivative, and I also have, for example, x squared plus 5 times the first derivative, and 5 times y equals 7, for example. This is a second-order differential equation. If I also have a differential equation that contains the third-order derivative, this would be a differential equation of third order. We can also classify differential equations based on their type, and we have two types of differential equations, ordinary and partial. An ordinary differential equation is an equation with ordinary derivatives that are not partial, whereas a partial differential equation is an equation containing an unknown function of multiple variables and its partial derivatives. Now let's give an example of this. An ordinary differential equation could be this one: the first derivative of f plus 3 times f plus x equals 0. Now, in order to have a partial differential equation, we need a multivariable function with at least two variables, for example, f of x and y. And an example of a partial differential equation could be 5 times the partial derivative of f in terms of x, plus, for example, x times the partial derivative of f in terms of y, plus xy equals 0. And this is an example of a partial differential equation. Differential equations are also classified by linearity, and we have linear and nonlinear differential equations. A linear differential equation is the equation that is linear in the unknown function and its derivatives, whereas a nonlinear differential equation is one where the dependent variable and its derivatives appear nonlinearly. So let's give some examples to make that clear. Can you spot which equation here is linear and which is nonlinear? Of course, the first one is linear because all of its components here and the function and its derivatives appear in linear form, whereas this one on the right is nonlinear because we have components, for example, raised in the powers of 2 and 3, and we also have the component of sine x, which break the linearity. Lastly, we have homogeneous and non-homogeneous differential equations. A homogeneous differential equation is one where all terms involving the dependent variable and its derivatives are of the same degree, whereas a non-homogeneous differential equation is one where the equation includes terms that are not equal to zero and do not depend solely on the dependent variable and its derivatives. So let's give an example of a homogeneous differential equation. This would be the second derivative, for example, of f plus the first derivative plus 3 times f of x equals 0. And this is a homogeneous differential equation. Whereas a non-homogeneous differential equation would be the first derivative of f plus 3 times f equals the sine of x plus e to the x. Let's try to classify these two equations based on what we saw. So the first one here, we can see that we only have a first order derivative, so it is a first order differential equation. We also don't have any partial derivatives, so it is also ordinary. Now, we don't see any nonlinear components, so it is also linear. And we also don't see any components that do not depend on the unknown function and its derivatives, so it is homogeneous. Now about the second one, we see that we have a second derivative, and this is the highest order derivative in the equation, so it is a second order differential equation. We also see that we do not have any partial derivatives, so this one is also ordinary. Moreover, we see many nonlinear terms. For example, the second derivative is raised to a power of third, or we have the logarithm and also the trigonometric function. So this one is nonlinear. And also we see components that do not relate to the functions and its derivatives. So this one is non-homogeneous. Well, that's all for now, and I hope you have a better understanding of the basics of differential equations, and of course, stay tuned for more.